Hello everyone, thanks for joining me for section 3 today, in which we're going to talk about graphing proportional relationships. Our learning target is I can write and graph proportional relationships. I want to start today by asking you in our section title here, it says proportional relationships. Well, what is a proportional relationship? What's a proportion? If you remember back last year or even maybe a couple years ago, you talked about proportions, and that's just an equation stating that two ratios are equivalent. So something like 1/2 is equal to 2/4. That's a proportion. It's saying that these two ratios are equal. And what we want to be able to do today is graph and write proportional relationships. So the first piece of information that we need to know talks about direct variation. And direct variation, it says when two quantities, x and y, so x and y, are proportional. So when these two quantities are proportional, the relationship can be represented by the direct variation equation y equals mx. That's our direct variation equation. And m is the constant of proportionality. Okay, the constant of proportionality. So that's really just saying that's the number that your proportion is increased by each time. And that might seem a little bit confusing now, but it'll make sense in a little bit with a few problems, I'm guessing. And before, you may have thought of the constant of proportionality as something different. But today, I just want you to kind of understand that you've seen this before. It's just been written in a little bit differently. So we can think of m as the constant of proportionality, or we can also think about it as the slope of our line, or we could also think about it as a unit rate. So m is all of these things. They're all essentially saying the same thing. It's constant of proportionality, it's the slope, and it can be considered a unit rate. And I'll show you that here in our next problem. Remember from last section, I shouldn't say section, last year, that when you have a direct variation equation, part of that stipulation is that your line has to pass through the origin in order for it to show direct variation. And in this case, our line does pass through the origin. But don't forget about that little piece of, or that little stipulation. Probably you learned that last year at some point, but it can be, it's just like a little simple rule, so it might have been easy to forget. All right, let's see what it actually looks like to graph a proportional relationship. It says the cost y in dollars for x gigabytes of data on an internet plan is represented by y equals 10x. It wants us to graph the equation and then interpret the slope. All right, so let's make first off, let's make our x and y axis. So y is my vertical and x is my horizontal. Okay, I'll label those. And y talks about the cost in dollars. And x talks about my gigabytes of data. So put data used, and we're talking about gigabytes. Pretty standard for a phone plan these days. It wants us to use the equation y equals 10x to graph it and interpret the slope. Okay, so the equation shows that our slope, the number that's in front of x, remember they called this m in the key idea, this is our slope. All right, and we know, since it shows direct variation, that it also has to pass through the origin. Okay, so what we're going to do is we're going to plot those two things and then connect them with a line. Right, so my cost looks like I'd be safe to go by tens. So here is 0, 0, 10, 20, 30, 40, and so on. And then the data used, I'll just go 1 gig, 2 gigs, 3 gigs, 4 gigs, 5 gigs, so on and so forth. Okay, and my first point is going to be the origin, because if that's going to be if I use 0 gigabytes, well, it's not going to cost me any money. How about if I use 1 gigabyte? If I were to enter in 1 for my x, because my data used to be 1, what would my y be? Well, 10 times 1 is 10. So when x is 1, y is 10. So I will enter in this coordinate point, 1, 10. Should be right here. Okay. If I use 2 gigs, well, 10 times 2 would be 20. So 2, 20. You can see that this is going to just follow this pattern. 3 gigs be $30, and so on and so forth. So there's how we can graph that equation. Just make sure you connect your lines and add the arrow to the end. Remember, we wouldn't do any negatives in this situation because it wouldn't make sense to have negative data used. So all of our data will just be in this first quadrant. Then it says interpret the slope. So what does it mean that our slope is 10? What does that mean in the context of the problem? Well, that means that our cost is equal to $10 per gigabyte that you use. Remember in the previous example where I said your m, or your constant of proportionality, can also be thought about as a unit rate. Well, for every 1 gigabyte that we use, it costs $10. That's what it means when it says interpret the slope. It means, what does this 10 actually mean in the context of the problem? It means that it costs $10 for every 1 gigabyte that we use. All right, here is another example, and in this case, they're using mainly a word problem to describe this. It says the weight y of an object on Titan, one of Saturn's moons, is proportional to the weight x. So the weight x of an object on Earth. Right? So when I see x, I'm going to think about Earth. And when I see y, I'm going to think about Titan. An object that weighs 105 pounds on Earth would weigh 15 pounds on Titan. Okay? It says write an equation that represents the situation. So first, I just have these 2 points. Let's take those points and write them as a coordinate point. Remember, a coordinate point is just x, comma, y. In this case, x stands for the weight of an object on Earth. So it says an object that weighs 105 pounds on Earth. So that's what I will substitute in for x would weigh 15 pounds on Titan. Okay, so remember I called y Titan, so 15 pounds for Titan. So there is our coordinate point. We know that if we were to graph it, this line would pass through 105 to the right and up 15. Now, can we use this information and put it in my direct variation equation? So remember, that was y equals mx. Well, I know one of my x points is 105. So I'm going to say, and I know my y is equal to 15. So I'm going to substitute in 15 for y equals m times, I know x is 105. Okay. I'm going to put a parentheses in there to just represent that I'm multiplying so it doesn't look too confusing. Last step here, let's solve for the letter m. So m is being multiplied by 105, so to undo that, I would divide by 105 on both sides, and m would equal 15 divided by 105 would simplify down to 1/7. I can divide each by 15 there. Okay, so my slope is 1/7. It wants the equation, so lastly, my equation, y equals, I figured out my m was 1/7, so 1/7 x. I'm just substituting this in to this equation. This would be my final answer. Okay, I used my 2 points to put it into y equals mx, the direct variation formula. I solved for m, and then I put that answer into my direct variation equation. Okay. So letter B asks, how much would a chunk of ice that weighs 3.5 pounds on Titan weigh on Earth? All right, let's use this equation that I just came up with to solve for that. How much would a chunk of ice that weighs 3.5 pounds on Titan? Okay, remember now, I called the weight of Titan objects y. So let's substitute 3.5 in for y then and solve for x, because that would tell me the weight of an object on Earth. Okay, here's my equation. What is being done to x? It's being multiplied by 1/7. So to undo that, I would divide by 1/7 on both sides of my equation. This would cancel. And remember, dividing by a fraction is the same as multiplying by its reciprocal. So 3.5 divided by 1/7 is the same as 3.5 times 7/1, or 7, and 7 times 3.5 would give me 24.5, and in this case the weight would be pounds, so lbs. So for something that weighs 24 pounds on Earth, that would only weigh 3.5 pounds on Titan. Kind of interesting. And in this case, it was that chunk of ice. Okay, why don't you go ahead and pause here to try 1 and 2 on your own and see how you do. All right, for example 1, when you're graphing this equation, again, we're staying in the first quadrant here. And now my slope is just 12, so I'm guessing you could, for the first, in example 1 where we went by tens, you could keep that similar. So you could go by tens again and go by ones for our gigabytes. It's going to be very similar, except now Our first point will be at the origin, and our next point will be at 112. So this is going to be a little bit steeper of a slope. 2 would be at 24. Okay, so on and so forth. You just keep going like that. And then interpreting the slope, what does that mean? Well, in this case, it would be $12 per gigabyte. And then in number 2, it says, in example 2, how much would a spacecraft that weighs 3,500 kilograms on Earth weigh untightened? So I'm still going to use my equation y equals 1/7 x, but now I know the weight of something on Earth. Okay, so I'm going to insert that in, or substitute that for x. So y equals 1/7 times 3,500. Multiplying by 1/7 is the same as dividing by 7. So 3,500 divided by 7 would give me a total of 500. And that would be kilograms for my weight there. So if an object weighed 3,500 on Earth, it would weigh 500 on Titan. Okay, moving on to our last example of today with comparing proportional relationships. It says the distance y in meters that a 4-person ski lift travels in x seconds. So you can see x seconds and y distance or meters traveled is represented by the equation y equals 2.5x. The graph shows the distance that a 2-person ski lift travels. So this one is a 2-person ski lift, this graph. And the first example tells us how fast how far a 4-person ski lift travels in x seconds. So notice we're comparing a 4-person by this equation and a 2-person by this graph. It wants to know for letter A which one is faster. Okay, so what I'm going to try to do is to figure out which one's faster. I'm going to try to find my slope, also known as the unit rate for each one. Well, for the 4-person, it's pretty obvious because it's just the number in front of x. So my slope, or my unit rate, is 2.5 for the 4-person one. And what does that mean? That means meters per second. 2.5 meters per second. The 2-person ski lift, what is this slope? Well, it doesn't tell us, but it's pretty easy to find. Remember, slope is rise over run. So if I'm here at 4 and I go up to 12, so notice I'm going by 2's here. 2, 4, 6, 8. I go up 8 and I go over. These are going by 1's. 1, 2, 3, 4. 8 over 4 gives me 2. So for the 2-person ski lift, that travels 2 meters per second. Which ski lift is faster? Well, that is the 4-person ski lift is faster. And if you think back to the ski trip, I would say that's probably close to true. The 4-person ski lift probably needs a little bit more energy or power to get 4 people up, so maybe that's why it goes a little bit faster. Okay. Looking at letter B, it says graph the equation that represents the 4-person lift in the same coordinate plane as the 2-person lift. Compare the steepness of the graphs, and what does that mean in the context of the problem? So I'm actually going to come up here and I'm going to graph it in this same one because this one already has the 2-person ski lift. graphed. I'm just going to show it here quick just for time's sake. If you want to use this one down here, that's fine. But it would just be a matter of copying this one down on the bottom one and then adding in the 4-person. The 4-person ski lift, it would start at 0 as well. And for every 1 second, it would go 2.5 meters. So 1 second, 2.5. So it's just going to be right above this line. Now for 2 seconds, how far would it go? Well, this times 2 would be 5. So it'd be right above there. Let me just kind of fill in for you. If you went to 4 seconds, maybe around the 10. So you can see it's slowly, gradually getting a little bit further away from the line. It's going to be a little bit steeper than the 2-person ski lift. And what does that mean in the context of the problem? Well, when you have a steeper line, that represents that is going faster. A steeper slope means that it's changing, your rate is changing more quickly. Okay? And we saw the same results as what we got when we looked at their 2 unit rates or their 2 slopes. Okay? All right, please pause now to finish the last on your own problem and come back to see if you got it correct. It says the table shows the distance y in meters that a T-bar ski lift travels in x seconds. Compare its speed to the ski lifts in example 3. Okay, so it goes 2.25 meters per second. So in other words, 2.25 meters per second. So that's faster. That's faster than the 2-person, but slower than the 4-person. So it's right in between the 2 from the previous example. All right, that wraps up 4.3 for us in graphing proportional relationships. Please come see me if you have more questions. As always, good luck on the homework, and I'll see you guys next time.